The universe has secrets. It whispers them across billions of light years. For centuries we have strained to listen. We built telescopes, our ears to the cosmos, each one better than the last. But on Christmas Day, 2021, humanity launched something truly special. We sent forth a new eye, a golden eye, designed to see the very first light of creation. It is called the James Webb Space Telescope, or JWST. It's our most powerful instrument for cosmic exploration. It orbits the sun 1,000,000 miles from Earth, far beyond our atmosphere. It's a time machine, and a truth seeker. This isn't just another telescope. Its giant honeycomb-shaped mirror is coated in a thin layer of gold. Gold reflects infrared light exceptionally well. We're all familiar with the idea of a black hole. It's a region of space-time where gravity is so strong that nothing, not even light, can escape. They are the universe's ultimate monsters, born from the collapse of massive stars. Most black holes we know are anchored in place. They sit at the centers of galaxies like our own Milky Way's Sagittarius A, holding entire star systems in their gravitational embrace. Or they are part of binary systems, locked in a cosmic dance with a companion star. They have a home. But what if some of them don't? Imagine a black hole violently ejected from its home galaxy. This can happen during chaotic galactic mergers. Two galaxies collide, and their central supermassive black holes do a gravitational dance of destruction. Sometimes one gets kicked out, sent hurtling through the void at millions of miles per hour, or perhaps a supernova explosion is asymmetrical, giving the newborn black hole a powerful push, sending it careening into interstellar space. These are the wanderers, the rogue black holes. How do you find a black hole? It's a fantastic question because you can't see them directly. They are black. Space is black. It's the ultimate camouflage. So astronomers have to be clever. They become cosmic detectives, looking not for the object itself, but for the effects it has on its surroundings. One way is to watch the stars. If you see a star orbiting around nothing, then you might have found a black hole. The star's frantic dance reveals the presence of its unseen gravitational partner. It's like watching a dancer twirl with an invisible partner. You know someone must be there holding their hand. Another method is to look for the chaos they create. When a black hole is actively feeding, the material doesn't just fall in quietly, it gets whipped into a frenzy. This material forms a disk called an accretion disk that spins around the black hole at incredible speeds. The friction within this disk heats it to millions of degrees, causing it to glow fiercely in X-rays. But these methods work for black holes that have companions or are actively eating. A wandering black hole is different. Enter the James Webb Space Telescope. This observatory is uniquely equipped for this grand hunt. While the Hubble Space Telescope has found some potential candidates using gravitational lensing, JWST takes the search to a whole new level. Its incredible sensitivity allows it to monitor millions of stars at once with exquisite precision. It can detect the faintest fluctuations in starlight, the very kind of subtle brightening that would signal the passage of a rogue black hole. JWST can stare at a dense field of stars for long periods, patiently waiting for one of them to wink at us. What makes JWST even more powerful for this task is its vision in infrared light. The center of our Milky Way galaxy is where we expect many of these wanderers to be, but this region is thick with cosmic dust which blocks visible light. Infrared light, however, can penetrate this dust. JWST can peer through the galactic smog and see the crowded star fields near the galactic core clearly. This gives it a much larger hunting ground, dramatically increasing the chances of catching a lensing event in the act. The process is one of patience and data. The telescope would be programmed to observe a specific patch of the sky containing millions of stars. It would take picture after picture, day after day. Computers on Earth would then analyze this mountain of data, comparing each new image to the previous ones. The software would be looking for a very specific pattern, a single point of light, a star, that smoothly and symmetrically brightens and then dims over the course of a few hours or days. The computers would flag any such event as a potential candidate for a rogue black hole. Imagine the scene at the Space Telescope Science Institute. It's a Tuesday in 2025. An automated alert suddenly flags an unusual JWST event. Data point GCRBH01. A star in a crowded galactic center field brightens tenfold, then fades over 72 hours. The light curve is perfect, smooth, symmetrical, achromatic. Same across all infrared colors. That rules out most variable stars. The team scrambles, pulling up every data set. It's an ordinary old red dwarf. No outburst history. The room is excited but skeptically tense. First step, eliminate every other possibility. They check archives, Hubble, ground-based telescopes, nothing. The lens is dark. From duration and magnification they estimate mass and velocity, estimated mass 7 times the sun, a rogue, a wanderer. The announcement comes on a Thursday morning. A press conference is called. NASA, the European Space Agency. The world's media tunes in. The lead scientist steps up to the podium, their face a mixture of exhaustion and exhilaration. They present the images, the data, the unmistakable light curve. They announce that the James Webb Space Telescope has made the first definitive detection of an isolated stellar mass wandering black hole. For the scientific community, it's a moment of pure triumph. The news flashes across the globe in an instant. How many? Where are they? How fast are they moving? Astronomers around the world begin pointing their own telescopes towards the coordinates, hoping to catch a secondary effect. The ghost has already passed, but the discovery resonates far beyond the halls of academia. Many times the mass of our sun, hurtling through the darkness, somewhere out there. It's a humbling and slightly terrifying thought. This single discovery acts as a cosmic Rosetta Stone. It allows us to start answering some of the biggest questions in astrophysics. By studying the mass, speed, trajectory of this rogue black hole, we can learn about the event that created it. Born from a specific type of supernova, parent star in a dense cluster, ejected from the galactic center, every detail is a clue about the violent processes that shape galaxies. Finding more would let us build a statistical census and paint a clearer picture of the life and death of massive stars. These wandering black holes could help solve the mystery of dark matter. One early idea: many primordial black holes formed in the early universe. The idea has fallen out of favor, but discovering many wanderers would force a re-evaluation. With many detections we can map their distribution and measure velocities to reconstruct the Milky Way's merger history. These dark wanderers are like fossils of ancient collisions, galactic archaeology with black holes as artifacts. Every detection tests Einstein's general relativity in the most extreme environments. Any tiny deviation could hint at a deeper theory of gravity. This single, silent object drifting through the void becomes a laboratory for fundamental physics. It's a testament to the cosmos's power to teach us, if we build the tools to listen and observe. Naturally, when we hear about a massive, invisible object hurtling through our galaxy, a certain question comes to mind. Is one coming for us? It's a valid thought, born from our instinct for self-preservation. The simple answer? The odds are astronomically low. Space is vast, the solar system is a minuscule target. Even if there are millions of wanderers, the space between them is almost incomprehensibly empty. We're more likely to be hit by a normal, untracked asteroid than by a rogue black hole. But imagine for a moment, what if one passed through our solar system? It wouldn't have to hit us to cause devastation. Its immense gravity would be the weapon. Passing through the Oort cloud, it would fling a shower of comets toward the inner planets, including Earth. If it passed closer, it could disrupt planetary orbits, potentially flinging Earth into a colder or hotter orbit, or ejecting it from the solar system entirely. The discovery doesn't increase danger, it confirms a hazard we already suspected. In a way it makes us safer, because now we know how to look. We have the tool, JWST. We have the method, gravitational microlensing. Future advanced sky surveys might map their paths, creating a warning system that spans thousands of years. The discovery of the first wandering black hole would not be an end. It would be a beginning. It would open a new chapter in our exploration of the cosmos. It would spur the development of new telescopes, new techniques, and new theories. Every new discovery in science doesn't just provide an answer, it reveals a dozen new, more profound questions. This is the engine of progress. What other secrets are hiding in the darkness? What other invisible phenomena are waiting to be revealed by the next generation of instruments? Perhaps there are wormholes or evidence of other dimensions or answers to the nature of consciousness itself encoded in the patterns of the cosmos. We don't know, and that's the most exciting part. It reinforces that the universe is under no obligation to make sense to us, but it has time and again revealed its secrets to our persistent inquiry. The search is what gives our lives meaning on a cosmic scale, so we must keep looking up. Each image, each data point is a postcard from a distant shore we may never visit in person, but can explore with our minds. The story of the cosmos is the grandest story of all, and we have only just begun to read its opening pages.